Good morning, everyone, and welcome back to day 6 of Pixapalooza. We're hoping you're all staying safe and staying sane in your respective self-isolation routines and quarantines all over the world. And we are happy to see that so many of you have come back to join us for this day 6. Today's topic is going to be look dev, performance, and profiling. We are going to do more of a technical deep dive into how to ensure we hit our target frame rates within Pixitope. We are going to be looking at fine-tuning performance and identifying bottlenecks. We're going to talk briefly about lighting, shadows, pre-computed versus dynamic lighting, as well as some best practices for reflections, best practices for ray tracing, as well as the ins and outs of video playback within Unreal and Pixitope. Before we move on, my name is Frank Daniel Moenvedvik. I'm a senior project specialist at the Future Group, and I'm delighted to take all of you with me on this trip to Pixitope. So this is the second to last day of our initial schedule for Pixapalooza. And here you can see the agenda as it is for this session. Before we get started, it's worth mentioning that this is probably going to be a more brief session. It's going to be a lot of technical information, and we're going to do more of a deep dive into subjects that we have already covered, but possibly skimmed over previously this week. Since there's going to be a lot of technical information, please ensure that if something is unclear, please ask us questions using the question methodology, question functionality within our webinar service, and we'll get back to you as soon as possible. And we will also be going through all the questions together at the end of this session. So on that note, let's dig into it. And we're going to start off by discussing the Pixitope render pipeline. Now, we spent a lot of time looking at the input and the output of Pixitope. If we change our feed, we actually, of course, have a live output feed coming out of Pixitope right now. And something that a lot of people often ask us is, what is the overhead? Because, of course, Pixitope does introduce some overhead. It's non-fluctuating and minimal. And mainly, our performance impact is dictated by the resolution at which you're outputting at, rather than what is happening in your scene. So the Pixitope specific overhead is very non-fluctuating. It just sits on top of everything else happening within Unreal. So something that is worth giving a special mention to is the fact that the performance impact that Pixitope adds can be a bit tricky to debug. It is not added to, for instance, the profile GPU widget within Unreal, which you can access hitting Control-Shift-, So you might have edge cases where you're using large amounts of inputs and outputs within Pixitope, where you'll start being unable to hit your target frame rates. But if you were to say, bring up your optimization unit, you'll be able to see that you're supposedly within your budget for milliseconds, but you're still not getting a clean, smooth output feed. Speaking of feeds, just so we clearly covered it, the actual 3 feeds you're looking at right now is, of course, my webcam. At my side, you're going to be seeing our live SDI output feed, which is sent out as a webcam feed, which is going to compress it, but make it run hopefully at a smoother frame rate. Below me, you're going to be seeing my actual screen share, which is going to be a lot less smooth, but hopefully better resolution. In these days, now that everyone in the world are doing video conferences, we sadly are experiencing some slight degradation of performance. Please rest assured that if you're seeing blurry video feeds, or if it's hard to keep track on what's happening on the screens, we will be making all the raw recordings of this webinar available after this session, as we've done with all the previous sessions as well. So you'll be able to review all this footage in full resolution at your own leisure down the line. Now, back on track. We were talking about performance. So The GPU visualizer is in many ways my go-to tool whenever I'm having issues with hitting my target frame rates. We are currently rendering at 50 FPS, which means that we have a budget of, I was about to say 20 milliseconds, but let's us verify that. Yeah, so our current budget is 20 milliseconds, which we are currently not quite hitting. But we can see that we are not actually being bogged down by what's happening in the GPU. We're also not being bogged down by what's happening in game or the GPU thread. These threads represent different things happening on a machine. The game thread is mainly concerned with what's happening on your CPU, whereas the draw thread and the GPU thread are concerned mainly with what's happening in the communication between your CPU and the GPU, and the GPU thread is completely concerned with what's happening in the GPU and the time it takes to render the graphics on your screen. As a general rule of thumb, not really a universal truth, if your game thread is lagging behind, that usually means that your CPU is bottlenecked, which typically points towards either too much happening elsewhere in your machine, too many applications running in the background, or simply that you are doing too much with blueprints, for instance, having too many blueprints doing things per tick, which can be excessively heavy and cause performance issues. If something is happening in the draw thread, that will often be that you simply have too many actors in your scene. If you have a few 100,000 individual actors which are not instanced in clever ways, that might cause draw thread issues simply because there's too many actors to draw every single frame. And if you have issues in your GPU thread, that might be anything related to sheer graphics. It might be too much overdraw, too many overlapping transparent particles. It might be too complex materials or too much transparency or too much parallax. It might be ray tracing. But it's generally a good place to start figuring out what's going on. But we're getting sidetracked. We're talking about, of course, the Pixeltope render pipeline. So let's see what happens if we exacerbate the Pixeltope issues. Something that we will often do in Pixeltope is add separate media inputs for virtual monitors. We might want to have 2 or 3 different virtual monitors, each of them having a separate SDI input feed, and we'll be adding those from the Pixeltope Director Setup tab underneath Configure Video Input Output. So we can see we already have one media input. I don't believe we need to make more. We can simply say that we're going to use this media configuration, and we're going to route this as a few separate inputs. So we are going to add this a few times. We can go ahead and change our, we're going to go ahead and change my secondary feed here because it's going to misbehave for a second. Okay. And we're going to go ahead and enable VisuVig, which should give us sort of a live preview of input and output. So what we can see now, since we have a lot of all the things going on, we're screen sharing, we are running ray tracing, we have a lot of things going on. Now that I've also gone ahead and added a lot of separate media inputs, we can see that our frame rate is now dipped down to unacceptable. Let's take a look. We're currently rendering 13.8 frames a second. This is simply because we've taken too much of the GPU overhead for the piece of media pipeline by adding a large amount of high resolution media inputs, which still, looking here within the Unreal interface, we have a hard time telling that exactly what's bogging us down. It seems to be related to the draw thread, but no matter what you do, you'll be having a hard time debugging exactly what's going on in here. Bringing up the GPU visualizer will show us that the render scene from the scene capture or track camera, which basically is VisuVig, is taking 65 milliseconds. But trying to break this down is not going to give us that much more information. It's going to falsely claim that this is related to shadow depths, which is simply not correct. So then we are just going to go back into our Pixeltope interface and just remove some of these unnecessary inputs. So now we only have two media inputs, one media input instead. I'm going to give the render pipeline a second to catch up. See, let's quickly go ahead and give this a reboot. We seem to have some lingering settings, which might happen sometimes. All right. So as we can see, adding these extra media inputs was quite deliberately done to tank our frame rate. So I'm just going to go ahead and purge it completely. We seem to be still having the inputs routed under the hood. I will probably need to restart directory to get rid of them, but this is fine for now. So in case you're wondering, how do we actually identify that this is now the GPU bogging us down? The easiest way to do that is to go into the task manager. Just simply go into Control-Delete task manager, bring in the performance tab, where we can easily visualize that here we see that our GPU is running at a breakneck speed capped out at 100, and this is probably the main reason why we're not hitting our target performance. If we were to restart director and maybe add one or two media inputs, as we keep adding media inputs, we'll simply see that we keep climbing and adding a flat rate for each additional input. The takeaway here is that the media inputs are great to use for live SDI input, but please be cautious and consider using alternate sources of media input if you wish to have a large amount of video sources. For instance, using streamed feeds over Ethernet, using stream media sources, or using pre-recorded video footage from video files instead. All right. So let's just go ahead and quickly restart the director, just to ensure we flush our routing settings. So the takeaway here is that each additional media input adds a GPU impact, but it's a flat rate for each additional input, and it's dictated by the resolution of the input source. So streams and pre-recorded video is definitely preferable to use, at least when possible. Unreal supports large amounts of real-time video playback, so it's mainly the Agile framework that tends to bottleneck us. This is going to be the one. So moving on, light, shadow, and reflections. We've looked at quite a few sets, some of which have been using live lighting, some of which have been using pre-baked lighting, and that's what we're going to be looking at right now. Since we're going to be playing with baked lighting, we are going to quickly slap together a very simple set, just because it's going to give us simply because it's going to allow us to do a bake in a short amount of time. So I'm going to go ahead and go to my dev folder, as I've done several times before. Let's just quickly make a new folder from scratch. And let's go ahead and make a new level. So what we're going to do here right now is that we are going to go ahead and we're basically going to build a little set. We are going to have a single light source. we're going to need a floor. We're going to add a few walls. And there we go. We're pretty happy with this. The last thing we're going to do is we're going to add an actor over here for us to look at. Let's just go ahead and find a static mesh, which is going to be our hero actor for this particular production. We're going to select something at random. Let us go ahead and add, say, this statue. Okay, so we've looked a lot at ray tracing. If we had ray tracing enabled right now, we've previously disabled it as we relaunched the director. If we had ray tracing, we'll be able to see some global illumination bouncing off the floor, occluding, well, giving some light, bounce lights on these walls, allowing us to actually see what's going on. As things are right now, we are using a single directional light source to light our scene. The light source is going to be set to be static, which is going to give us these preview warnings in the shadows, informing us that Unreal is expecting this light to be baked, and we're just simply seeing a preview of the light. If we were to set this to movable, you see the resolution increases slightly and the preview goes away. Turn it off, you see resolution goes down, and movable resolution goes up. So if we are to have a fully dynamic scene where we're using lots of dynamic moving lights, then all of them have to be set to movable. But then we have issues like this where we don't get any global illumination. What you then will typically do is things like adding fake bounce global illumination. So saying here where since there's so much bounce of these far walls, we're going to add some bounce using, for instance, point lights. We could take a point light, center it. Since this is going to be a fake light source, we don't really have to worry about the physical properties of the light anymore. We could turn off inverse square fall off. We could go ahead and turn off shadows. And we could go ahead and do something like this to give us some fake bounce. Doesn't really look ideal. We'll have to do some tweaking to make this look acceptable. But now we basically have a fully dynamic scene where we could start animating all of these properties on the fly. We could easily, during runtime, rotate our directional light if we wanted to emulate a moving sun, and so on and so forth. But if we were to hit now Control-Shift-, to look at Profile GPU, let's actually go ahead and turn off VCVig so we have less variables to consider here. There we go. Let's also lock this predefined position using Control 1 on a keyboard, which is going to allow me to hit 1 at any point in time to snap back to my locked predefined camera position. Now, since there's not a lot going on here, we can look in the lights tab, that we're currently using 0.37 milliseconds for lighting. This is not really going to be very variable. If I were to do a recheck of this, we can see that we're still at 0.37 milliseconds. This is fine in the current scenario, but it's easy for a directional light in a more complex set to be using a lot more performance. A directional light could easily be using 10-15 milliseconds if your set is complex enough. Each geometry you add, casting shadows, will add to the complexity. Each shader, especially transparent shaders and using ray tracing, will also add to the complexity and render cost. And a single directional light could quickly become debilitating. It's also the fact that this is not very physically correct. GI is all faked using a fake bouncing point light. To work around this, we have the option of baking our light. Baking lights is probably the single most performance optimizing thing you can do in a virtual set in terms of having a one-click solution to just give you an acceptable frame rate. Baking a light means that we are going to be rendering a separate path of textures for every surface in our scene called light map bakes. To access the light baking, you simply go to the Build tab at the top, hit this drop down, and you choose Build Lighting Only. We have a few settings here. We can choose the light quality. Doing a high quality light bake, especially on production settings for a large set, can take several hours. So for now, we're just going to lock this at preview, and we're going to quickly review our light bake settings. Underneath world settings, if you scroll down a bit, let's see even further past all our compositing, you'll be able to access light mass, where you can see all our different light bake settings. Here you can access things like light bounces. We can see different thresholds and fallouts. If you're going to be using volumetric light maps, which basically allows us to light moving things as they move through 3D space with irradiance probes, you can set the resolution of these probes here. And it's basically just a full kit for fine-tuning your light bake settings. There's a lot of guides online to help you fine-tune these sliders for your particular production. For now, we're just going to go ahead and leave this as is. We're not going to touch any of the bounces. We could actually probably take down the indirect lighting bounces to 1 or 2 because there's not a lot of complex shapes. And then we're just going to go ahead and run a build. When we run this, Unreal is going to start up a swarm agent, which would allow us to do a distributed light bake across multiple machines if we have that set up. So if you have a large amount of studio machines, you could easily set all of your machines up to be helping out with your light bakes, allowing for much faster turnaround times. Let's see here. Let's try this one more time. It didn't seem to start. So you can see the build is running and we have, let's see. So I can see that our bake failed to complete. Let's quickly review why this is happening. First, we're going to check and make sure that we don't have any force node pre-computed lighting enabled. We do not. Then we're going to check our light sources. And as you can see, I changed it to dynamic and never changed it back, which means that we don't have any light sources expecting to be baked. You see, we didn't see the handy preview text. Thank you. So now let's do this one more time. Build lighting only. So what's happening now, we're gathering the scene, we're distributing to all our render machines on a local network, and now we have our final light bake. So now we're going to snap the predefined position, and we can see now that we have a pretty decent light bake. We can see some obvious issues right away, but let's first look at what we gained. First of all, by hitting Control-Shift, we can see now that there is no longer a light tab here. Lighting is currently using 0 milliseconds. We have completely removed the render cost of our lighting, which is fantastic, especially if in a typical scene, lighting can easily take 10-15 milliseconds. If you can shave that off, that is amazing because it means you can add more geometries, more shaders, more of everything else. So now let's take a look at some of the obvious issues here. We can see that our light bake is very low resolution. We can see that we have massive chunky pixels. Let's hit Alt-6 so we only see the lighting, which is going to remove the shader details, allowing us to get a closer look at the light bake in our model. You can see that our model also has some issues. We have some artifacts in the areas of finer detail. And it also has the same sort of low-res artifacting issue. Now, in many sets, having low resolution light bakes is actually a much smaller issue than you might think. Because when you start having geometries with complex shaders, it's a lot harder to see those lighting artifacts. At this range, we are able to see some of the artifacts on the podium of this statue, but it's really hard to see the actual smaller artifacts you saw on the fingers, despite them seeming rather egregious. But the environment itself is unacceptably low resolution, so let's go ahead and start resolving that now. So the way that light bakes work is that we bake things down to light bake textures. You can actually visualize these by going to world settings. scrolling down to the same tab as before, light mass, where if you expand at the bottom, you can see the actual light bakes for our scene. All the geometries in our scene have now been packed and baked as light maps in different channels. So this is actually multiple geometries packed into a single atlas. We can see that this section here is probably a part of the statue, just because it looks more organic than all the other planes. And the resolution for each geometry is dictated by the light map resolution for each individual geometry. All of these cubes are instances of the static mesh cube in engine content. And this cube has a default light map resolution of 64 pixels. This might seem like an outrageously low resolution to quite a few of you, but generally speaking, you can get away with a very low resolution for most geometries, simply because you just need an overall feel of the light. You don't really need pixel perfect lighting, except in certain edge scenarios. Let's go ahead and select all these geometries, and we're just going to override the light map resolution, which you can see immediately degrades our light map. And we're going to go ahead and set this to, say, 1024. This is an incredibly high value, but there's not a lot going on in the scene. We only have our walls, which can be considered hero geometries. So it's fine to spend a bit of extra texture resolution on those walls. Let's give this statue the same treatment. Set the light map resolution for the statue to 2048. Let's save our scene and quickly do another bake. Another good benefit of doing light baking is that it means you no longer have to worry about performance in terms of choosing which light sources to use. We've previously discussed that point lights are a lot more expensive than, say, spotlights. Area lights are again more expensive than spotlight, and directional lights have a very high performance cost to them. But the moment you bake your lighting, all of this goes away because the lights are no longer resolved during runtime. So you can see here the bake is taking a bit longer simply because we're calculating more pixels. Let's go ahead and let this finish up. I think for the next few run-throughs, we're going to slightly dip down the resolution. But this is more in line with what you can expect when you do your own light bakes. The light bakes take a lot of time, so it's good to keep them in production quality and ensure you have a render farm available, allowing you to more quickly spit out previews of your light bakes. Now, here we go. We can see now that we resolved the majority of our issues. We can see we have a nice crisp shadow on the far wall here. We can see that we have nice bounce lights and GI in the corner. This here is actually correct ambient occlusion. It's not caused by our post-process volume giving us fake AO. See here, if we go into our post-process handler, search for ambient occlusion. Let's just ensure this is turned off. There we go. So we saw some fake AO, but all the AO we're seeing now is physically correct. So this looks rather lovely. We also see we have a nice drop shadow from our statue. And we can see the majority of the issues in the light bake in the statue, if we hit Alt-6, have also gone away. No real further work needed. Very nice. We can see that we have some artifacts, we have some noise, especially here in the intersections. But if we were to do a render with production quality settings, all of these artifacts would also go away. Now let's start looking at how this is actually done. In order to do a proper light bake, every single vertex, all our geometries need to have unique UVs. We can open the statue, we can take a look at the UVs in the static mesh by looking at UV channel 0. And as you can see, this geometry has unique UVs. And UV channel 1 is going to be the light map UVs, which is simply the same UVs but packed with more padding. Great. But what happens if we do not have unique UVs? Let's quickly go ahead and create a 3D geometry which has mirrored UVs, which is very common for a lot of geometries that you are optimized for games. And let's take a look at what will happen with that geometry in a light bake. Let's just quickly go ahead and make, say, a simple shape like a cup. There we go. Let's go ahead and give that a nice bevel. And then we are going to unwrap it and use this within Unreal. And then we're going to review what happens with our light bake. Now, this is not a 3D modeling session, so let's try to be a bit swift about this. That'll do. Now we're going to mirror our UVs. So we're just going to quickly go ahead and delete our right-hand side. Something like that. We are going to quickly just create some UVs. Let's go into our UV editor. As you can see, now we have some nice UVs for the inner and outer shell. And then, as we will often do when we create our geometries, we're simply going to go ahead and mirror this actor. And we're going to put this into Unreal. Let's mirror this on the y-axis. Let's make sure it's welded. And just like that, let's go ahead and hit File, Export FBX. And put this into our scene. Let's go into our dev folder. Let's go into, I don't actually have the browsers up, so I just quickly need to bring one up. There we go. Let's go to our documents and pull in this new geometry. So in the FBX import settings, we are going to ensure that we are not going to generate light map UVs. We're going to talk about what this does at a later point. We are going to leave everything else as is, and we are going to go ahead and not create any materials and textures. Nice. So you can see we have some UVs. They're not exactly very clean. We probably should have done a cylindrical unwrap, but for the sake of a light bake, this should suffice. Well, we're going to put it here halfway in the light and shadow, like so. Let's go ahead and lower the resolution of the light bake on our cubes just so it finishes faster. Let's dip it down to, say, 512. Let's now go ahead and hit build and do a new light build. It's worth mentioning that there's nothing stopping you from using a combination of dynamic lights and static lights at the same time. In case you were wondering what the downsides of baking light is, it's the fact that you cannot move a geometry with baked lighting and expect the baked light to stick. Luckily, you can have a scene where you're using baked lights for all your lockdown environment actors. And then you can have your movable actors, like if you're doing a car production, you can have moving cars which have dynamic lights being received. You can have a virtual set where the virtual monitors that roll in and out are dynamic actors receiving dynamic lights, while everything else in the background is static. We're going to take a look at that in a second. So here we can see that we immediately get a warning telling us that this object, the S cup, has overlapping UVs. They overlap by 50%, which makes sense given that they're perfectly mirrored. And let's see what happened to our light bake. Now this looks a bit gnarly. Give me a second. Sorry about that. The reason we have these artifacts is because one side of the cup is in the shadow, the other side is in the light, and we are trying to bake that same data, the light and the shadow pixels, on the same UVs, which means that random pixels get selected and we get this mess. Any of you that have done any kind of baking to UVs in the past have probably seen this before. This is what happens when you have overlapping UVs. And this is why you need to make separate light map UVs, as my colleague Jonas touched upon in a previous session. Now, this might be a huge turnoff to a lot of us. If we have a virtual set that we already have built, it has 2,000 unique actors, which we've modeled and imported. It's going to be a massive amount of work and effort to start tweaking all these geometries and generate new light map UVs. Luckily, there is a utility within Unreal allowing us to generate light map UVs on the fly, which is being done by default when you import a new geometry. That was a checkbox I turned off earlier, which was generate light map UVs. What this checkbox will do is it will take your UVs, as we see here. It's going to unpack them. It's going to take overlapping UV islands, separate them, and then it's going to pack them as closely as possible based on your light map resolution. So when it comes to UVs, the space between the UVs for a geometry is typically called the gutter, or sort of the dead space. Generally speaking, if you have, let's say, an expected texture resolution of 1024, then you're going to want to separate all your islands so that with mip mapping, there's going to be more than one pixel between them at your chosen resolution, so that if one island is going to be texture red, the other island is going to be green, you're not going to see any bleed across. This is going to be a lot more drastic at a lower resolution, because then the gutter needs to be bigger to ensure that you don't have any bleed. Having low resolution light maps is fine, but then we have to ensure that one island which is completely in the shadow does not spill over to an island which is completely in the light. So now if we go ahead and hit generate light map UVs, then we will go ahead and click apply directly underneath that checkbox, which is going to be, let's take a look. I always forget where that is stored. That's going to be underneath load 0, so it should be somewhere here. Oh yes, apply changes. So we enabled generate light map UVs, then hit apply changes. And with a fraction of a second, we can see we now have a separate UV channel 1, which is what we by default is what's used for light map UVs. And here we can see we now have a nice looking unpacked UV. We can also see there's a pretty big gutter. If this is going to be, for instance, a hero asset where we know that we're going to need a higher light map resolution, I could go ahead and set this. The minimum is going to be 1024. I hit apply changes. And now we can see these islands are packed a lot more closely together, giving us more effective space. Now let's go ahead and try this. Let's go ahead, build lighting only. Let's take a look at how this looks. We can also see that the cup is still being lit despite now no longer having a light bake applied. We're still generating a new light bake. The reason we are seeing the cup still lit is because of our radiance probes, or basically our 3D volumetric light bake. As soon as this finishes, let's take a look at that as well. Let's see, I'm getting some echo from your hands. Just about done here. While we're waiting on this, let's take a look at our volumetric light map as well, which you can visualize underneath Show, Visualize, Volumetric Light Map. So this is a pretty cool feature. It's going to be updated in a second here. And as we can see, we have all these different spheres which represent volumetric light captures. You can see here we have an issue with the cup in that I actually failed to save it. So the light bake hasn't, the UVs weren't updated. So we have the same issue. Let's resolve it in a second. But for now, let's take a look at our volumetric light capture here. So all of these probes or these spheres are going to visualize if I were to put a sphere here, this is how it would be lit based on the irradiance probe in the region. So here, if I go ahead and pull in a piece of geometry, like let's grab a skeleton mesh. As you can see, despite this character being dynamic, as we move him into the shadow, the character is still being lit correctly based on the baked lighting. So this goes to show that there's nothing stopping you from using dynamic lights and static lights in conjunction with static geometries as well as dynamic geometries. As we move our character out here towards the bright wall, we are getting more and more bounce visible here. Let's bring up the textures to see how it looks with textures on. Oh, he's still compiling. That's fine. Let's also go ahead and see what happens if we pull him over the ledge, where as we are no longer getting any bounce lights from the wall based on the irradiance probes we were visualizing. If I am to pull him over here, we can see that the moment we go up, we are no longer getting the bounce light, and we're now getting a completely black front-facing side. Okay, so we're going to go ahead and do one more take on this cup here to test our new UVs. In order to improve our light bakes, what we are able to do is pull in what's known as, let's actually find it manually. Let's go to volumes, and let's go ahead and pull in a light mass importance volume. This actor is used to tell Unreal where do we actually want to do a light bake. This will greatly speed up the time it takes to do a light bake because it will tell the engine that within this space is where we're actually trying to do a light bake. This is where we need to focus our calculations. So I'm going to go ahead and use this actor to box in our set. There we go, which is now going to greatly speed up our light bake process. We're also going to visualize a bit some of the artifacts you get from having this lower resolution preview bake by adding another source of light, geometry light. Another very interesting aspect of baking your lights is the fact that you can actually emit lights from not just light sources, but also glowing geometries. I can, for instance, grab any complex geometry, like let's say this tree shape. Get rested against the wall here and make it highly emissive. Let's go ahead and dim down the directional so we get more out of this glowing tree. Let's give it a bit of glow. Not going to do anything too crazy. We're simply going to go ahead and plug in a emissive value and give it a nice hot orange tone. If you wish to use emissive, use glow basically using emissive objects for your light picks, simply select those geometries and enable use emissive for static lighting in the actor settings. You can find this underneath details. It is not active by default. So if you have emissive objects that you don't see affecting your light pick, that is probably going to be why. It's a bit hard to see how strong this glow is, so I'm quickly going to tab into director and just ensure that we have convolution-based bloom enabled. That's going to be under effects. We're going to enable some bloom. There we go. So we can see we have some glow here. I'm pretty happy with that. So let's go ahead and do a test light pick. So we should now be seeing a much faster turnaround time for this bake, simply because we've limited the area that we're trying to bake. It's not going to be drastic because there is not anything else in the scene to begin with, but this can be a highly efficient time saver if you, for instance, have a virtual set with a large surrounding area that you don't actually need the same kind of shadow fidelity as you do in your talent position. It also improves the quality of your light bake, simply because having this tight volume gives us a smaller range that we need to focus our light baking attention on. So each pixel is going to be sharper. So you can see here this turnaround time was much faster. We're just wrapping up this light bake now. And this is despite having now a secondary complex light source, which is this glowing tree. Typical issues you'll see when you're doing preview light bakes is, for instance, that lights will sort of bleed through thin geometries, typically seen in virtual apartments where you will see lights bleeding through the walls at the corners and shadows clipping through. Okay, that is fairly typical fare and not something to be concerned about if your high resolution production ready bakes turn out better. So we can see here that our light map UVs are correct and we actually did save the geometry. The problem is we forgot to refresh the light map coordinate index of this cup, which is why it still looks a bit gnarly. This is how we tell the static mesh which geometry, which UV it's supposed to be using for its light bake. If you are generating a light map UV on import, it will automatically be set to the correct index. But since I did it manually, at no point was this set to be pointing at the new light map UV we generated, which is stored in index 1. So I'm going to update this to 1. I'm also going to override the used resolution to 1024. We're going to go ahead and save it and do one last try at this. While this is going to be ticking along, we're going to look at what we got from the last light bake. You can see here that our tree is now casting light in the environment in a gorgeous way. This is simply not something you can do with dynamic lighting. Let's also try to move our geometry closer. You can see that as we move it closer to the glowing geometry, we actually start getting that glow onto our moving object. Very nice. And this is going to be replicated correctly in 3D space. And all of this is given to us due to the volumetric light map. You see here, we have this nice warm glow coming off this tree. You see it here on the side as well, which really does give us a lot. If this is something you wish to use extensively, if you're going to have a lot of glowing objects in your scene, you can go ahead and go to world settings, go underneath your light mass settings, and you can simply increase the density of these reflection probes. You can see right now they're spaced about 2 meters apart. Instead, you can go ahead and tighten that up underneath. Let's see here. underneath volumetric light map detail size, where you can simply tighten up the cell size. If I set this to 100 meters, it's going to quadruple the resolution of a light map, but it's basically going to give me a lot more probes, giving me more reflective lighting. As you can see here, we have one probe at the left of the tree and one at the right. So you can see that our statue, as we move past this probe, it gets darker despite coming closer to this glowing tree source. If you increase the light map detail cell size, this behavior is going to get more accurate. You can also see that finally we've got the correct UVs on our cup here, and now our light bake is looking a lot better. You can see it's a bit dark inside, which then could be improved by increasing the amount of bounces. So we will have more light bouncing off the far side of the cup, lighting up these shadow areas. But of course, there's also the fact that the actual material on the cup is very dark and gray, so there will not be that much bounce light to go off in the first place. And this is more or less a brief overview on how to use light bake within Unreal and Pixeltop. Now let's go ahead and take a glance at reflections. We've used reflections extensively over this past week. We reflected all kinds of things using all kinds of different reflections. But let's take a deeper look at what these reflections cost and what they actually do. In order to do so, let's go ahead and get a reflective floor in here. Let's go ahead and make a shiny metallic floor with a normal map, just so we get some interesting breakup. So we're going to go ahead and set the roughness to 0 to make it perfectly reflective. We're going to make it metallic to ensure that the reflection picks up the color of everything we reflect as well. We're going to make the base color a very non-realistic value of 1. Actually, let's give it a 0.88, which is the PBR value of snow. And let's see if we can find a detailed normal map just to get some interesting breakup in our reflection. We're just going to go ahead and take this tiling normal map. We're going to scale it a bit using the UVs and simply multiplying it up a bit. We'll plug this into our UV coordinate. We're going to flatten these normals because if we were to plug this directly in, we can see it is going to be overly strong. As you can see, it's a bit too bumpy. So I'm going to use a flat normal node. Set the flatten value to 0.2. Sorry, 0.9, and plug this into our normal. It's actually a bit too flat, so it's fine for now. Okay. So now we've created our shiny floor. Let's apply it on the ground here. And we're going to start with the most commonly used type of reflection, which is going to be screen space reflections. You can see now there's not a whole lot going on. We're not really seeing any reflections at all, which is because we haven't turned anything on. Let's go to our post-process handler. Let's search for reflection. And we can here see underneath reflections, we're going to enable screen space and set them at, let's say, we're going to give them an intensity of 100. So a screen space reflection is a rather cool kind of reflection because it's so incredibly cheap. With this enabled, we can see we have nice reflections in the entire scene. And if we were to open our GPU visualizer, look in post-processing and sort by performance impact, I'm not even sure if we'll be able to find the cost of screen space in here. No, but it's going to be incredibly performant. Screen space reflections cost almost nothing. This is as opposed to planar reflections, which we've looked at before. We've concluded they are very expensive, but we're going to do more of a deep dive of that in a second. We can see some obvious issues here though. We can see that, first of all, we have this sort of strange black halo at the sides. This is going to be a lot less noticeable if this area was filled with another color than pure black. For instance, if we had, let's say, a sky sphere, I believe we might have one underneath our engine content. If we had, I believe this might actually be excluded from reflections, but if we had some atmospheric fog instead, interesting. Okay, nevertheless, if we had the geometry up above, I'm simply going to take the floor and move it up. I'm going to nil out the material for it. There we go. So now, as we finally can see, we now have something to fill in some of these blacks. But we still see the issue here at the edges. Now, the reason we are seeing this issue, that what we're actually looking at here is the limitation of screen space reflections. The way screen space reflections work is that by using a combination of the depth buffer and the actual color buffers within the Unreal pipeline, we're able to sample a pixel. We're going to see what the corresponding pixel is going to be based on a screen space reflection, or basically flipping the image, so to speak. And this is going to allow us to flip for this floor whatever the corresponding pixel is above and use that as a reflection. The problem is, what if the pixel we are supposed to reflect is out of frame? We can see here we have a black halo at the bottom, and if I were to tilt my camera down, the less of the white wall we see, the less we are going to be able to reflect. When I'm finally tilted all the way down, there's simply not going to be any data for the screen space reflection to work with. In many use cases, this can be fine, especially if we are never going to do any crazy angles like that. But if we are ever going to do a low tilt, we can see why this is no longer acceptable. This is a very extreme use case. We are going to be looking at this in the studio scene later. You see that the artifacts can be a lot less noticeable than what we're seeing here, but this is just to highlight the limitations of the method. We can go ahead and look at how we can adjust screen space to give us more or less bang for a buck. We currently are looking at a screen space reflection quality of 50%. This is giving us low resolution. I believe it's doing a less frequent capture, and it's probably ignoring some render features. The lower we bring this, you can see the less accurate our reflections become. Inversely, the higher we pull this towards 100, the better our reflections become. We now have more sharpness, we now have better resolution, but the overarching issues are still present. We don't have any extra data to reflect, which gives us pretty gnarly issues. Something we could do as a kind of a fallback here is to use something like, for instance, a sphere reflection capture, which immediately helps fill out a lot of these black spots. The way a sphere reflection capture behaves is that it actually does a 360 capture based on the position of this actor. So here, if I hit build reflection captures, this acts as a 360 camera capturing the environment around it, and it projects that as a 360 capture. Let's go ahead and take a look at this separately by turning off screen space. So you can see now that right now, the entire reflection on the floor is as if we're reflecting from this point of view. So if we put our camera exactly here and look around, It's going to look pretty decent. But if I am to put this over here by the wall, we're now going to get a very disproportionate reflection. It's going to look like the wall is directly left to me because the wall is directly left of the screen space reflection capture actor. But if now we use this actor in conjunction with screen space, we're finally starting to get something that might be acceptable to use in real time. We can see now that the black artifacts we were seeing at the edge before have been filled out with the screen space reflection capture, which means that we no longer have obvious artifacting black holes, but we can still clearly see the transition where we go from screen space to our fallback method. We can see that some actors like our statue and our glowing tree disappear when we are falling back to screen space, as well as our cylinder and our reflections of our talent here, which is to be expected because all of these are very regional reflections. Okay, now the last thing we're going to look at is going to be the most, well, besides ray tracing, the most expensive kind of reflection actor we can use, which is going to be the planar reflection actor. Let's go ahead and pull this in. And immediately we can see, I'm going to go ahead and pull the percentage of this to 100% for the planar reflection actor. And just off the bat, we see something that looks really good. We now have incredibly accurate reflections, despite not looking at the actual talent. We can see we're reflecting something which is off screen. It's being correctly broken up by the normal on the floor. It is very resilient to artifacts caused by, for instance, temporal aliasing. There's no temporal aliasing artifacts to speak of. And it reflects things like shadow and light perfectly. This is our go-to reflection actor for most of our productions, just because it gives us something that to most people is going to be indistinguishable from physically correct ray traced reflections. The way it works is that we have a plane, which is the planar reflection actor, which simply acts as a mirror. The way this functions is that we take the entire scene, we flip it over this actor as a mirror, and we render the scene again flipped across this actor, so in this case upside down, and this is what we're using for our reflections, filtered through the normal map of whatever we're seeing reflections through, of course. There's a few obvious limitations here. For instance, what happens if our floor is not a plane, or what happens if our floor has multiple planes or multiple levels? Let's say here that on the left side, there's going to be a step up. Let's go ahead and add a second layer to our floor, like so. And let's go ahead and drag in the reflective material on the left-hand side here as well. Immediately, we are starting to see some issues. Where reflections are connecting very well for this cup, we can see that here on the higher level, there's a disconnect. We can actually see a gap between our cup and the cup and the reflection. The same thing is visible here for Gideon from Paragon. There's a spacing between our talent and the reflections on the floor, despite the fact that we can clearly see that he's actually standing on the ground. The reason for this is the reflection is mirrored across the plane reflection actor. It's not actually using the geometry as the reflection plane. So if I were to take the plane reflection actor and move it up to this new floor, you can see we're actually offsetting our entire reflection to this new floor. Moving it up is going to resolve the issue up here, but now we have another offset in the other direction down on the base level. Where you can see here, the offset means that we are not actually seeing this podium being reflected at all. So this is a pretty big and obvious issue. There's ways we could work around this. We could, for instance, have one planar reflection actor for each separate floor height. Before we go ahead and do that, let's take a look at the render cost of our planar reflection actor using Control-Shift, comma. We can see here that our reflection plane actor is currently using 3.17 milliseconds. Please remember this number. So I'm now going to go ahead and adjust the distance fade out here. We are going to tighten this up so we are not going to be able to see the reflections from this higher plane on the lower floor. And then we're going to go ahead and add a secondary plane reflection actor for the lower floor. So you can see, since we tightened up the distance here, the planar reflection actors will no longer affect the different heights. There we go. We can also adjust parameters for reflection actors. I can, for instance, say that the higher plane, I don't want to interact with the normal map of the floor. I want it to be more flat. So I can simply turn off normal distortion strength, which is going to make the reflection ignore the normal map of the floor itself. You can also set each individual plane reflection actor to have a higher or lower screen percentage, which is going to minutely affect performance. So here, where we have a lot of normal map breakup, we might not need to use full screen percentage. So if I were to set this to maybe 50%, we don't really see much difference, which means that 50% might be fine for the lower floor. If we were to do the same thing on the upper level, where we have a perfect mirror surface, we're going to see a lot more artifacting in the reflection because it's easier to see the individual pixels. So this is not acceptable, so we're going to keep the upper level at 100%. So now we can see that we have perfect reflections on the upper and lower level, but we do not have any reflections here on the side. So let's go ahead and add 1/3 planar reflection actor for the side here. And we're going to go ahead and rotate this 90 degrees. And as you can see, we now are actually getting correct reflections on the side as well. I'm just going to go ahead and ensure that screen space is turned off. Very good. Okay. So there we go. Now we have reflections on the side here, on the floor, and on the higher floor. So given that one planar reflection actor took 3.17 milliseconds, we should be, of course, assuming right now that we are currently using about 9.5 milliseconds on reflections, because we are doing this sort of flip technique 3 times instead of 1 time. Let's take a look at our GPU profiler. And here we can see that for this first reflection actor, it's actually a lot less because it's probably reflecting less actors. The second one is also very efficient. Let's see, wait a second, this can't be right. Wait a second. Interesting. So I'm going to now go ahead and delete. I'm deleting the 2 first plane reflections, so we only have 1 right now. Okay, so I guess we had something else up and running earlier, because you can see now the actual render cost of this single plane reflection actor is 1.25. But then as we add the other ones back in and do the same test, we can now see this finally. We can now see that this first plane reflection actor, which before cost 1.25 milliseconds, has now more than doubled. It's now costing 2.71 milliseconds. We can see that the two other planar reflection actors also have slight cost connected to them. But we can see that we are doing more than just adding the cost of these actors together. The reason for this is each additional planar reflection actor is also going to have to render the reflection in the other reflection actors. This means that we start multiplying cost. If you have one planar reflection actor, you have to draw your geometry 2 times. If you have 2 planar reflection actors, you have to draw your geometry 4 times. If you have 3 planar reflection actors and all of them are visible from the camera at the same point in time, you're actually at this point drawing your geometry 8 times. In this scene, there's not really any geometry to speak of, so the render cost is going to be insignificant. But in a complex scene, this is going to get debilitating very, very quickly. So generally speaking, you're going to try to want to limit yourself to 1 or 2 planar reflection actors at the most, if at all possible. But do keep in mind though that here, let's say that we only want to have our hero reflections up here on the top. We could go ahead and delete the lower ones. We could go ahead and re-enable screen space reflections. We could then go ahead and go into our modes tab, find a a sphere reflection capture. In this case, since we are using such a square scene, instead of doing a 360 sphere capture, we can actually use a box reflection capture instead, which is more suited for square environments. Then we're going to go ahead and build our reflection capture. What we are looking at right now is the 3 different reflection types we've been looking at so far, used at the same time in beautiful unison. Up on the top, we are going to be using the highest fidelity reflection type, the planar reflection actor, which you can see here. And then on the lower level, where the planar reflection actor doesn't reach, Unreal is going to jump back to the fallback, which is going to be the slightly lower level resolution type, which is going to be screen space reflections, which we are seeing here. As you see, when I move the camera down, we lose the top of the tree as well as the statue, telling us these are screen space reflections. And when this happens, we fall back to the most basic reflection type we have available, which is going to be our box reflection capture that we just created. So together we have now been able to utilize the pros and cons of all the reflection actors at the same time. Very good. Before we move on, just one last cursory glance at our planar reflection actor. Please note that if you're going to be using this actor in a very complex set, you might of course notice that the moment you pull it in, you tank your frame rate by adding 10, 20 milliseconds to your render time. What you can do is go into your planar reflection and do a more granular control setup of exactly what you're trying to reflect. So the great thing about the planar reflection actor is, since we are drawing the scene again, we're not just sampling pixels. This means that we can choose what we actually want to draw. Underneath the scene capture, underneath the planar reflection actor, we have a lot of very nice granular controls where we can choose what we want to reflect. Let's go ahead and see here. We have our atmospheric fog, which, let's see, build. Okay. So as you can see here, if I were to say disable atmospheric fog, it's a bit hard to tell because it's using the fallback immediately, but you can see at the rim, it stops rendering the atmospheric fog in the reflection. I could go ahead and do things like disable lighting, which might be fine if you have a very rough reflection or baked diffuse lighting. So I could go ahead and turn off basically dynamic shadows. Sorry, that's going to be. Yeah, this might actually be correct because we're using baked reflection captures. Sorry, we're using baked lighting here. So let's say if we are mainly using baked lighting, but we also have a strong directional spotlight like so, casting lots of shadow. You can see here that turning off dynamic shadows and reflection is going to make the spotlight bleed through, but we still get the shadows from our baked lights. The reason this might be a good idea is because here, if you enable dynamic shadows and take a look at the cost of the planar reflection actor, which is now up to 5 milliseconds, we can break this down. And we can see that a significant chunk of that is shadow depths, which is currently 30% of our overall render time for this particular planar reflection actor. Breaking it down even more, we can see that all of this cost, which is 0.43 milliseconds, is caused by the spotlight. So simply turning off this dynamic shadow, which is going to cause some light to bleed through at the back, but which is going to be completely invisible from up front, more or less, gives us half a millisecond better performance, which is significant. And then one of the last things you could do is something we'll often need is just to have planar reflections for our talent or our hero actors and not for anything else. So here we could either go ahead and just search for the show flag for static meshes and turn it off. So now we're only reflecting our skeletal mesh, which is this 3D character. Optionally, we could instead go here to the primitive render mode, set it from legacy mode where we are rendering everything to use show only list. And then we could go ahead and add an actor to the show only list, which means that we are only going to render the actors visible here. I'm going to choose a static mesh. And now the planar reflection actor is only going to reflect our talent, which is this particular 3D model. If we hit Control Shift comma and look at our planar reflection, we can see we're now down from 4.8 milliseconds to 1.16 milliseconds just by turning off shadows and using the show only list. You can also see we have some artifacts here caused by screen space reflections. We could spend some time and try to rectify that, but I think it's time for us to move on. The next thing we're going to do is to look at more high quality reflections and lighting. So we're going to go ahead and kill the scene. We're going to jump out of the editor. And we are going to go ahead and enable ray tracing. As we all know, using ray tracing, turning it on can be very costly. It's going to add a lot of overhead to the render time despite using a state-of-the-art GPU. The way we work around this is we selectively enable and disable features as we need them, so we don't ray trace anything more than we have to. So then what we need to do is choose what do we need to ray trace and what do we not need to ray trace. So let's go ahead and go to the launch menu, go to the setup tab in Director. Let's go to General. Let's enable DXL mode. Let's go ahead and hit Launch, hit the drop down, and fire up our scene, which is going to be Level Studio in Editor. Now we're seeing a whole lot of beautiful light radiance probes. So here we can actually see the baked light in this particular set. But this is a bit disorienting to look at. So let's go ahead and get rid of these probes. Light, show, visualize, volumetric light map. There we go. Okay, so in this particular set, if you hit Control Shift comma, you can see that we have planar reflection actor eating up 15.16 milliseconds of performance. And the rest is caused by our geometry or in our base pass. I'm just going to quickly go ahead and delete our planar reflection, which is again being used for talent position up on stage here. So by deleting that, we can see we lose our planar reflections. that's fine, because instead we are going to be using ray tracing. So jumping into live mode, I'm going to hit F11. We're going to decouple ourselves using F8, and now we can fly around freely. Let's actually not do this in full screen, just because we are going to want to have slightly better performance as we look around here. I'm going to bring in my FPS counter, my unit graph. So let's go ahead and bring in my stat FPS as well, just so we have something to look at. So hitting Control-Shift, we can see currently we have pretty good performance. We have visibly disabled. Let's take a look here. Okay, so the reason we are tanking is mainly because of the overhead of drawing the UI as well as some of the pixel pipeline, but generally this is a good starting point. Now let's go ahead and start enabling render features. Let's go ahead and turn everything off. No, sorry, turn everything on. We're going to be working with the console, which you're going to have to if you're going to be manually toggling ray tracing features on and off. So we're just going to go ahead and turn on r.raytracing.shadow, set that to 1. We're going to turn on r.raytracing.reflections, set that to 1. And we are going to turn on r.raytracing.translucency, same as transparency, set that to 1. And lastly, we are going to turn on r.raytracing.translucency.refraction and set that to 1. So now we can see that we have not quite as ideal performance. We can see that we are down from 30 to 20 FPS. Let's hit Control-Shift, and see what our performance is being eaten up by. So we have a few big chunks which are going to be our obvious suspects. Translucency is eating up 6.62 milliseconds. Reflections is eating up 10.21, and lights is eating up 2.90. Now, in this particular set, we are supposed to be using baked lighting. We have baked lighting set up. We've done a light bake, so it doesn't make sense not to use it. Because when you think about it, a light bake is actually ray tracing, but just not in real time. It's still a ray traced lighting environment. It's physically correct GI. It has just been pre-computed and baked down to textures. So you should absolutely not be shy of using baked lighting. So all we have to do then now is, we can see here, over here on the side, we are now using ray traced lights. You can hit Alt-6 to see them kick in. Instead, let's fall back to our baked lighting. So I'm going to type r.raytracing.shadows, set it to 0. And now we simply fall back to our light bake. And as a result, if we pull out and bring in Control-Shift, again, it's not drastic, but the impact of our light impact has gone down ever so slightly. The reason it's not a 0 value is simply because if you look at our actual lights in our scene, let's pull this down a bit. You can see all the backwall spotlights on the sides are static. But we have here and there a few dynamic spotlights as as made obvious by the orange dot. Signified, thank you. Okay. Next up is let's take a look at the next thing we can optimize, which is going to be our reflections. So right now we are currently using ray trace reflections. The most easy way to optimize our reflections is to limit where we're actually using ray trace reflections. So what we could do is we could set up screen space and planar reflections for areas like this large floor, as well as a talent position. instead of using expensive ray trace reflections, which also have issues with noise in areas of large amounts of roughness. It might be hard to make up, but if you look closely here, we can actually see a bit of noise, especially as I move the camera, in this orange reflection. So what we could go ahead and do then is type r.raytracing.reflections. And here, if you dot, we now have a lot of more granular controls. We could choose whether we want to ray trace height. We can limit the distance for our reflection rays, which is going to optimize a bit. We can, for instance, turn off ray tracing for, well, we can turn off ray tracing for shadows within reflections, which is going to optimize things a bit. Or we can simply say that I'm only going to apply ray tracing to any surface which is very shiny or just about that shiny. I'm going to make a roughness cutoff threshold saying that anything which is rougher than this value is not going to get ray trace reflections. Let's set this to something like, first of all, here, max roughness. Let's say that the max roughness is going to be 0.2. Now we can see that the reflections for the floor went away, and we can see that the curve drastically improved. Let's go ahead and turn it back on. Keep an eye on the curve here. We can see that we dipped all the way back down to 14.6 milliseconds, sorry, for FPS, and we are flatlining in terms of performance. Let's set it back to 0.2. There we go. So now we have much better performance. Let's actually set, and then we can start trying to fiddle until we find a value we're happy with. So maybe something like 0.4 might be good. So we get some ray tracing in metal fixtures like this. So we get that nice sort of interaction with the carpet. That might actually be a bit too much. Let's do 0.3. There we go. So now we have a little bit of ray tracing where we pick up some of the carpet here in the wall fixtures. Some of our more metallic surfaces up on the talent position are still ray tracing, but the larger surfaces like this wooden floor, the carpet, the brick wall are no longer ray tracing reflections, greatly improving our overall performance. Next up is the glass and transparency. Translucency is notoriously incredibly expensive as well as noisy in ray tracing. Looking at this glass, which also is going to look incorrect because this glass has been made with a lot of shader tricks, optimizing it for non-RTX, like messing with semi-metallic values and refraction settings, which don't hold up when you're trying to ray trace and treat it as physically correct glass. But we can also see that there's a lot of noise and there's a lot of performance impact. If we pull in so the glass fully frames our scene, like for instance this floor podium, we dip all the way to 12 FPS, 11 FPS, whereas looking back up brings us up to 40 FPS. We could go ahead and say that, you know what, we don't want to ray trace any transparency within the scene. So we just search for r.raytracing.translucency and set it to 0, which actually improves the look and feel because it gets rid of our artifacts. And it also greatly improves the performance looking at these transparent surfaces. But let's say that you have something like this here position here with this glass table where ray tracing actually adds a lot. Now, again, this particular glass shader is not really set up for RTX. Luckily, we have a glass shader we are prepared in advance for this particular use case. So just go ahead and replace the glass on the surface. I believe it's going to be, is it this one? I don't think it's this one. It's probably, it might actually be this one. Let's go ahead and give this a second to compute. There we go. So here we can see that for this particular surface, ray tracing the glass adds a lot. Let's turn it on and off again just to see the difference. So you can see this is really night and day. We get that refraction. You can see we are actually warping the metal bars visible to the glass. We can see they're picking up shadows from the glass surface. We can see that we're picking up the red heat from the metal, as well as the orange of the couches, which is being colored by the glass itself. We can see that we are diffusing things a bit, as there's a bit of diffusing or opaqueness to the glass itself. We can see that we get those lovely hot pings from the spotlights up above. So ray tracing this glass table, if this was our hero position, would be absolutely crucial. So this means we need to dig into more granular controls. So let's see what we can do here. Now, a typical problem is that some of these things you can turn on and off might not make sense to us. We might not be familiar with the term. We might not understand what it does. We might need more information. It's good to keep in mind that with any any console command within Pixscope and Unreal, if you, instead of a value, just add a question mark at the end, in the console, it will spit out a description of what the function is, as well as what the valid inputs are. In this case, ray tracing refraction is going to enable refraction in ray traced translucency. Default value is 1, and that is what is going to allow us input. So now if we go ahead and set this to 0, we're turning off the refraction, which somewhat improves our performance, but also removes our refraction. This might be fine for certain kind of glass surfaces, especially flat surfaces, where you might not have a large amount of refraction in the first place. Like here, I feel like it actually looks overall a bit better, so I'm going to go ahead and leave that turned off. Next up is we can see that we are having some biasing issues. We can see that, especially as we get close, we are getting these nasty black artifacts, which also greatly affects our overall performance. This is caused by ray bias. I'm not going to try to explain exactly what that means because I'm not an authority on that subject. All I know is that if we happen to adjust our primary ray bias value, let's go ahead and hit the question mark just to see a description of what this does. So it's a long technical description, but the takeaway is that the default value for this is very low, 0.0001. Bringing this to higher value is going to remove our shadow artifact issues, but it's also going to risk having just thin transparent geometry sorting in the wrong order. Let's go ahead and set it to the max of 1 right away. As you can see, this actually greatly affected performance. We've gained at least a few frames from that. And the artifacts you saw, the black halo, the black pixels, are now completely resolved. So just like that, with a few console commands, we have greatly improved the performance of our ray tracing for this glass. We also end up with an aesthetically more pleasing result. You also see it here over on this edge frame. We're no longer really seeing any artifacts or noisy pixels, but we're still getting that nice, physically correct ray trace reflection. Very nice stuff. All right. The last thing we're going to do is, we are going to do a cursory glance at video playback, and then we're going to look at optimization. We can see here in this set that as we look around, especially towards the left-hand side, for some reason our performance is skydiving, which is quite interesting. On the right-hand side, we have a frame rate of 34 FPS. Looking left, we have a frame rate of 22 FPS. And this is one of many things we're going to learn how to identify and resolve when we go into the ins and outs of actually optimizing a bad set. Before we do that, let's take a cursory look at the media framework. Let's go ahead and jump into the set we just created. We're not going to save any of this. Great, and all we're actually going to be looking at right now is just a bit of media playback. I'm going to go ahead and pull in a plane, just so we have something to look at our media on. Sorry, that's going to be a plane. There we go. It's going to be 1.6 by 0.9. Let's turn off locking, there we go. And we are just going to go ahead and add our media video component. This is the old one, which is legacy. We are actually going to add, sorry about that. Now, new one, the one down below. And we're going to go ahead and add the basic media actors for this brief cursory glance. So we're going to need a media player, MP video. We're going to need a media texture, MT video. And we're just going to go ahead and put that in on our surface here and use that as a debug texture. Then we're going to need some media sources. We're going to have a file media source. And we're going to have a image media source. So the main thing we're wishing to look at right now is basically the difference between using videos, different types of videos, as well as image sources, and what the pros and cons of using these are. Okay, so the first kind of actor we're going to add is just going to be a video file. So we're just going to add a scissor wheel, we're going to save it, and we are going to go ahead and simulate our scene, open the media player, and we're going to play the media source we just added. Give this a second. It's a bit sluggish for some reason, probably because I'm doing a lot. There we go. And now we are playing our media source. So the interesting things here is, of course, we have a video file. This is, I believe, an H.264 encoded MP4 file. And as you can see, we can play it. We can fast forward it multiple times. But if you fast forward too much, you'll start having stuttering issues. And very importantly, we can play it backwards. Or can we? Let's take a look at this. Let's go ahead and make a blueprint just so we can control all this logic using blueprint logic. Let's pull this into our scene. Let's go ahead and bring in a reference to the media player we're going to be working with. So let's simply make a variable for media player. There we go. MP video test. And let's go ahead and assign the media player that we just created. It's this one. We can't see it in this list because it lives in our dev folder, which means it won't show up in search. And now let's go ahead and add some logic. So the main thing we want to test here is what can we do with these video files. So we're just going to first things first, the moment we start simulating, we're just going to play our video. So we're just going to open the source. The source is going to be the video source we just added. Let's just drag it in there because I can't add it from the search. There we go. And then we are going to go ahead and try two things. We're going to try to fast forward a video file, and we're going to go ahead and try to rewind a video file. But before anything else, I think we're just going to do a quick 5-minute break, just because I need to go and look after something. So we are going to take a 5-minute break here before we start doing this deep dive into materials. So let's reconvene at 11:48. All right, apologies for this short intermission. Let's get back on track. Just going to give you a few seconds to gather up your runaway colleagues, and then we will resume. So just to reiterate what we are looking at, what the focus of the thing we're doing right now is to see what do the different media and file formats offer us in terms of playback flexibility. In order to test this, we're going to be looking at two different video file formats, just as a cursory glance, as well as image sequences. So we're just going to go ahead and make a simple blueprint allowing us to actually play back our media file in different ways. First of all, we're going to open our video source. Let's actually use, instead of open source, we're going to use the open source with options, which is gives us a bit more options to choose from. Let's go ahead and right-click the options field and promote this to not a variable. No. Undo. Let's right-click this and split the struct pin, allowing us to choose the input values. So what I'm going to do is I'm going to say that I want to enable play and open, which means it's going to autoplay when I open the video file. And I'm going to allow it to loop indefinitely. So I'm going to go ahead and hit compile, save. And the last thing I'm going to do is ensure that this is actually playing the correct media source, which is going to be media source video. Compile, save, and now we're off to the races. The two things you want to test is going to be, we are going to test fast forward or FFV. And we are going to test PX rewind. So these are going to do two different things. Fast forward is basically going to set the play rate of this video file by an arbitrary amount. Let's go ahead and make a variable for that so we can play with this on the fly. Make a float called play rate. We're going to make it public so we can edit it on the fly. By default, we're going to give it a value of 3, so we play 3 times as fast. We're going to get the value and simply connect that to our set rate, which I believe is going to set up, yeah, that sets our playback media rate. Holding over any node will just give you a tooltip telling you what the purpose of the node is. And rewind is going to set the rate to -1, which should play it backwards. All right, let's go ahead and take a look at our media playback utility here. Let's put a media handler in a scene. Let's go ahead and hit simulate. And here we can see our video playing. Forwards is playing rock solid, it's smooth and nice. So let's go ahead and set the play rate to 2 and hit fast forward. It might be hard to see, but if you look at the webcam output feed, it's still rock solid and perfectly smooth. Let's go ahead and set the fast forward rate to 3. It's still working as intended. This is a 1080p, I believe it's a 30 FPS video file, by the way. No, nothing, some compression, but nothing extreme. So when we go to 4, this is when we start having issues. At this point, the fast forward is a slideshow, so we can tell that the safe range stops somewhere around a play rate of 3. Not 23, 3. All right, let's go ahead and set it back to 1, and let's try to rewind the video file. So let's go and set the play rate to -1. And at this point, it's a complete slideshow. So rewind, we can conclude, simply does not function. It's unwatchable, unplayable. This is not something you can use in production. The reason for this is that most modern video file formats are designed to be played in one direction only. That's why you have pardon if my terminology is not on point, but you will regularly have your keyframes. And then any data between these keyframes are simply how do these frames differ from the set keyframe. So it's always a forward-facing playback process. That's how modern video compression works. When you now choose to play things backwards, you're going to start bumping into hairy situations. But this is an issue with video files. But what if we weren't using a video file? Let's say instead we wish to use, say, an image sequence. Image sequences are going to take up a lot more space on disk. They're going to be a lot more bandwidth intensive because each frame is going to be an uncompressed image, as this image sequence we have here. But there's also big benefits of using image sequences, especially in terms of the freedom they offer us when it comes to playback. Something we didn't look at here is seeking and jumping to frames, but this is also a huge issue with video files in that it's hard to have frame accurate seeking and jumping simply because you will often start slipping frames. Again, some note here that these image frames are actually compressed. These are PNGs, they are not uncompressed EXRs, but I think for this particular showcase, it should be fine. It's just worth mentioning that uncompressed EXR files will read faster. But given that these are, let's see, properties. Yeah, given that these are HD image files, that should be perfectly fine. So let's go ahead and open the media source image actor we added. Let's go ahead and go to sequence path and try to find our, let's see, documents, downloads, I believe. Pixel image sequence. We're just going to select the first image in our sequence. We're going to go ahead and save that. And we're going to go ahead and tell our blueprint to be using this image sequence instead of this movie file. compile, save, and play. So here is our image sequence. So you can see here that what's the frame rate for this? Do we actually set the frame rate? We can actually here go ahead and set frame rate. So I'm just going to go ahead and force this to be locked to 30 FPS. And let's go ahead and play this one more time. There we go. So this is pretty smooth. We can see that there probably might be a tiny bit of stuttering caused by the fact that we have to uncompress a large amount of PNGs. Let's go ahead and play with this media playback. Let's first of all set the play rate to, let's see, it's currently set to 1. Let's go ahead and set to 2. Let's go ahead and set to 3. Let's go ahead and set to 5. Let's go ahead and set to 10. So the first thing you can see is a bit, of course, the clip is a bit too short to really tell, but using image sequences, we no longer really have a cutoff on a play rate. Setting it from 1 to 10 works perfectly fine. Setting a play rate to 100 is still probably playing back correct, except it looks like bogus because we don't have enough of a frame sample size here. But if we had a longer sequence, we would see that fast forward is no issue, which is great. This gives us more freedom in terms of building media playback that can be changed on the fly to do fast forward, seek into timeframes, and so on. Seeking image sequences is also easy to do. You can get frame accurate seeking because you are simply jumping to a particular EXR or PNG file. But what about rewind? We set our playback to -1. And as you can see, playing backwards is just as easy as playing forwards because we are working with full frames. And this is great. Now, this basically means that if we need to do more than just simply hit play and play a video file at a set frame rate, image sequences are superior. Now there's one last use case we wish to look at, which is what if we want to use something like HAP encoded files. HAP is a pretty new video codec standard, but one of the cool things about HAP is it allows us to embed alpha within our video files. If you're going to see that in action, we're going to actually have to make a new material called mHap test. Let's go ahead and open this. We're going to be using the same media texture, but now we're actually going to use our RGB as the emissive color. And we are going to go ahead and set this to be translucent, unlit. And we're going to take the alpha of our video file and plug that into opacity. I'm also going to go ahead and delete the media video component. Instead, we're going to be using this new texture I just created. The media source is now going to be our new HAP file instead, which is I believe, let me take a quick gander. This might actually be 4K. Properties. Yes, so this is a UHD 60 FPS HAP encoded file, which has alpha encoded in it. Now, I believe if we try to play this, we will simply have a failure to launch. We hit preview live. Well, first of all, I haven't replaced the actual video file. Let's open the media handler and simply go ahead and replace the video file we're trying to play back as the target media source. Now, if we try to simulate this, we can see that we are immediately, I believe, no, we're not getting an error. It's simply giving us a silent failure to launch. The reason for this is if we wish to use HAP encoded files, we have to go to our project settings. And we have to go ahead and enable, we have to go to plugin settings. And we have to go ahead and search for HAP and enable HAP media. Let's go ahead and do that and restart our level. We're also going to go ahead and enable a few useful project setting variables in order to improve our media playback behavior. So now we have HAP enabled. We are also in the wrong levels. Let's go ahead and jump to the level we just created, which I believe is going to be, now what did I call it? This is a bit embarrassing. I should probably be cleaning up a bit more efficiently between my sessions here. Let's go ahead and filter by level. Let's go ahead and look in all folders, including developers. And it's probably going to be light bake. There we go. Okay. So now if we hit preview, oh, and this is one of the wonders of using experimental codecs. It can be a bit finicky. We're going to give this one more try. Let's see. So that was called light bake. So let's go ahead and favorite that level just so I can find it by filtering by start levels. Let's also, before we go ahead and try to play this again, let's also go to our project settings, because this might also be something I have to do. If you search for media in your project settings, you'll see that you have a low latency mode, as well as hardware accelerated video decoding. These two are enabled simply because I have HAP codec enabled, but I might also need to enable low latency. Let's try this one more time. Okay. Okay, so it seems like we have some issues with this experimental integration of HAP, so we're not going to spend too much time trying to get this up and running. It might be the video file, it might be this particular version of the plugin, but it's worth mentioning that you can use it. We have used it, but right now we seem to be having a bad day. The summary, though, of using HAP is that it's even more limited than standard video files. It actually does not support reverse playback in any way, shape, or form. And it also is a lot more performance intensive. But I think at this point we're happy with what we concluded, which is that image sequences are ideal, but of course there's more of an overhead creating and using them in production, whereas video files are more compact, but gives you less playback flexibility. Okay, at this point, let's just move on. And the last thing we're going to look at is all the things we learned today. Let's put it to use and optimize a bad set. Let's ensure that we have ray tracing turned off. Let's go to the setup tab. Let's go to general and turn off ray tracing. And now let's go ahead and launch our scene, which is going to be Level Bad Studio. Ray tracing might also have been why the HAP video will refuse to play now I think about it. Oh well. So now we are going to look at a use case which probably quite a few have bumped into or will bump into the future. What happens when you receive a set that has been made by a third-party vendor? You're supposed to use it in a virtual production, but it is notoriously unstable and poorly performing. The set we're going to be looking at here is going to be incredibly performance heavy and as well as incredibly unstable. So we're probably going to have to try a few times to get up and running. And the goal for this session is going to be ensure that we can get this set to an acceptable level of performance in a very short amount of time. So the first thing we need to do is go to World Settings and turn off Vysiwyg. There we go. As we know, by default, if you have VSwig enabled, allowing you to get a real-time SD output feed, it will, of course, give you the SD output feed, but also double your render time. Now that we have that disabled, if I go to optimization and bring in my FPS counter, we can see we have a comfortable 8 FPS in this large view. This means that with VSwig enabled, we're probably running at 3 or 4 FPS, possibly even 2 FPS, which at that point you might start risking bumping into unexpected crashes, which is not really ideal. So now let's assume that this is a set we received from a vendor, and our goal is to go from 50 FPS to 50 FPS or higher by the end of the day, so we can actually put this studio on air. So the first thing we're going to do is figure out what is our bottleneck. As it's going to be in pretty much 95% of your use cases, the moment you bring up unit graph is typically always going to be either the draw thread or the GPU thread. It's very rarely going to be a CPU issue unless you have a grossly underscaled CPU. So you can see here that our draw on the GPU thread is clocking at a not so comfortable 140 milliseconds. Next thing we're going to do is we're going to fire up Control-Shift, to run GPU Profiler. So off the top here, we see a few things. First off, shadow depths. Our lights are currently using 70 milliseconds, which tells us that we probably don't have any baked lighting. Next up, we can see that we have 2 planar reflection actors, which also is not ideal. We can see that we have incredibly crisp reflections on the floor here, which is probably one planar reflection actor, and we have a second one up on the stage. So the first thing we're going to do is simply kill the extra planar reflection actor and use only the one on the stage. So in this set, we haven't actually set up our talent yet. Sorry, we haven't actually set up our video I/O. So we are still using a debug video feed. Just to make it more pleasing, let's pull this down on the floor so we don't have Pierre hanging in there. Very good. Let's pull a bit closer and over to the side. Let's also go ahead and go to the Modes tab, Pixeltope, and just quickly add a Versus Studio. Where is it? Let's go ahead and add the, oh, sorry, that's not something you add. Let's go ahead and select this center cone. Right click, let's convert this to Virtual Studio Floor, which doesn't work unless we do it on the actual actors themselves. Let's see, let's try this in a different way. So you can't actually do the right click and convert method to so you can't actually right click blueprints and do the convert to say AR or Virtual Studio or whatever, which is a bit of a shame. Interesting. Okay, let's not spend too much time messing with the comp. Let's just pull out a talent and get back on track here. There we go. Okay, so the reflections. Since we have 2 planar reflection actors, we actually have 3 of them, even worse. We have one up on the stage, we have one here on the floor, and we have one last actor up on our upper position. So what we could do is, instead of having all these visible, we could make a blueprint that toggles between them as we move around. But for now, let's say we are on the clock, so we're just going to do the bare minimum necessary, which is going to be to delete the ones we're not going to be using. Then what I could do, if I still want to have some reflections down here is I could go ahead and go to our volumes. And I could, instead of using a plane reflection actor, I could drag in a, sorry, that's not a visual effect. I could drag in a box reflection capture instead, pull it a little bit up, and simply save a level and do a box, build reflection captures box. There we go. So now we still have some reflections, but it's a box reflection capture instead of a planar. So now let's go ahead and profile again. We can see that the shadow depths is now clocking at 30, but we're also using an incredible amount of performance on just our base pass, which is our geometries and our materials. Let's first take a look at the geometries by hitting Alt-2 to go to wireframe mode and look at our wireframes. And here we can see that something is incredibly off. As you can see, as we look at our geometries, they look to be incredibly subdivided. Like here, things like our stairs, the floor, the wall, everything is just a solid wireframe. So we can see here that the polygon density has for some reason been incredibly exaggerated. Something that's interesting is that this density is visible everywhere. It's every single surface seems to be tessellated. A tessellation is something you can do in a material or a shader. So this implies to us that this is a shader issue. So we're just going to go ahead and find any material, for instance, this wooden material on the stage, and then we're going to open it. Then we can see that this is a child of a massive material called MMRAO. This particular material is a master for a large amount of materials in our scene. As a matter of fact, this single shader is being used on pretty much every single material used within this level. We are not actually even able to set a limit to the width, but we can assume that there's probably hundreds, if not thousands, of material instances like this wooden floor or these concrete slats that are based on this material here. Okay, so let's take a look here. We are currently running at a frame rate of around 40 milliseconds. Let's go ahead and open Material MRAO, and let's see what's going on in here. We saw that we had a large amount of triangulation, which implies to me that there's an issue with tessellation. And we can immediately see that there's a tessellation multiplier input, basically a subdivider, which is set to 64, which is insanely high. And this is also not dynamic. If you're going to use tessellation, you should absolutely base it on the distance to the camera. So the closer the camera pulls the surface, the more you tessellate. We could pull in here like camera position and tessellate as the camera pulls closer to something. But I think for now, we're just going to say that tessellation is going to be set to 0. We're going to go ahead and save this, which is going to take a while because it's going to have to recompile all the child instances. Let's go ahead and give this a second to think. And when this is done, we are going to, first of all, review our frame rate as soon as the shaders are done compiling. But we can immediately see that we are down from 40 milliseconds to 30 milliseconds, which is a huge improvement. Another way we could have been able to see that this was a shader issue is if we went to under lit optimization view modes, and if we were to look at shader complexity. Just gonna have to wait for our shaders to finish compiling, which is gonna take a second here. This is a very useful view mode because it tells us how complex is a shader. The closer shader goes to white, the worse it is. When the tessellation was set to 64, we could assume that most of these surfaces, which are now green, were previously probably pure white. Now you can see that things are performing a lot better. Everything is nice and green. And as we go back to our lit view mode, we're now actually gone from 40 milliseconds to 20. So simply changing that tessellation value, so you can see here now everything is much more low resolution, has drastically improved our overall render time. Very nice. But we still have some issues. So our milliseconds looking down here is now currently 20 ms, but as we go ahead and pan over to the left, we can see that something on the left side is killing our performance. We are now back at 45. So on the right side, it's smooth. On the left side, it's at tanking 45 milliseconds per frame. This tells us that something over on this side is killing our frame rate. Because of course, if it's off, if it's not being rendered, it shouldn't really add an impact. If we go over here and look at the wall, we're going to be locked at 20 milliseconds, which is where we're locked at just because that's our target frame rate. If I were to go to Video I/O and Director, go to Routing and actually remove my input signal, as well as my output signals, give this a second. Now you can see now we're actually going below 20 because we're no longer locked to our target render frame rate. We can see now we're actually rendering 10 milliseconds. So killing your routing might be a good idea if you're trying to test performance, because then you're not going to be locked, have a lower threshold of whatever your target frame rate is. So now you can see now there's actually a difference between looking down here, which is running at 16, and down here, which is going to be running at 10. Or down here, which is going to be running at 40. So let's try to figure out what's going on over on this side. So something over here is running at 40 milliseconds. As I dollar over to the left, we can see the performance improves. So it's not the stairs, it's not anything up here. It's definitely something in this corner. Looking at the wireframe, we can see that some geometries are pretty high resolution, but there's pretty high resolution on this side as well. Let's see, maybe it's a carpet. It could be the carpet, but the carpet itself seems to be running fine. The chairs seem to be running fine. The issue seems to pop in when we're looking at this wall. Interesting. Let's go back to our optimization view mode and let's take a look at the shader complexity and quads. Nothing really seems to stand out over on this side. We can look at the overdraw. This is useful to figure out if you have particle effects which are killing you. There is nothing sticking out here either. And at this point, we can't really tell from this buffer what's going on. But something seems to be up with this wall. So let's take a look at the shader for this particular wall. So that's going to be the Material Instance Grand Stair Stone Cladding. Let's go ahead and open this. And something that should be a clue is that we're actually seeing a bit of a slowdown directly in this viewport. Let's go ahead and open the shader for this. Actually, yes. So we can see here that there is some tessellation happening for the wall, but that should be fine for just a localized area. But here we have a pretty big clue. This giant node is something you will be seeing a lot of assets that you might buy from marketplaces, like the Unreal Marketplace or in example content. This is parallax mapping. It's basically a way of generating fake depth to make a plane or flat surface look three-dimensional. You can see we have this beautiful slat wall over here. We can see it's casting shadows on itself. It's being lit correctly. But what you don't know is that this surface is actually just a plane. If you look at this in lighting only mode without the material, this is simply a planar surface. If we go very, very close and zoom in, you'll actually be seeing that all of these slats are simply parallax occlusion. It doesn't hold up close, but the moment you pull out a bit, it looks absolutely gorgeous. And it doesn't have the performance impact of actually having all of this as 3D geometry. The interesting thing is at the right-hand side, this is perfectly smooth. At the left-hand side, this is tanking. Let's go ahead and see if we can find the same material on the right-hand side and open that as well. And here we have another clue. There's a separate material on the right-hand side and the left-hand side. So let's go ahead and compare the values on these two material instances. Let's try to frame this the same way. And here we can see something. On the right-hand side, the max steps is set to 32. The shadow steps is set to 32. And we can see that these values are being used in this parallax occlusion mapping node as input. But on the other side, these same values are set to 4096. What this means is that the parallax effect on the left-hand side has 4,000 layers, which is insanely computationally heavy. It means per pixel is doing the same parallax operation 4,000 times, which, as we might guesstimate, is not really going to be good for performance. Even a value of 32 is actually rather high. We're going to set it to 32. We're going to save it. Let's take a quick look here. Did we actually offset the correct values? All of this seems to be in order. Let's just ensure that we actually looking at the right material by opening the slats here. Definitely seems correct. Actually, well, sorry about that. It was actually just compiling the shader. As you can see now, the performance on the right-hand side is 40 milliseconds. On the left-hand side, it's 40 milliseconds. So you can now see that adjusting this last value drastically improved our frame rate. So the simple fact that we had incorrect shader settings on the left-hand side, which by itself took us from 40 milliseconds to 40 milliseconds. These are the kind of things that will kill your performance if you're not being careful. Let's now see, we can now see that pulled out in a nice large frame. We're running a lot better. We've gone a long way from the original 130 to now running at 56 milliseconds. And we can see now that the largest remaining issues we have are light scattering as well as lights. This tells us that the issues we have now are volumetric fog, which is what light scattering is a part of, and light, which is just the fact that all the lights are probably dynamic. Let's first go ahead and select our fog. We see we have exponential height fog, which has volumetric fog enabled. Volumetric fog can look pretty nice. So before we go ahead and kill this, let's see if we can improve our performance by baking our lights. You can see here that all our lights are now movable. So we're going to go ahead and select all our light sources and just make them dynamic and do a quick light bake. So we set these light sources to be static. We're going to take these light sources and set them to be static. We're going to take these light sources, the directional light, the spotlight. Oh, we can't do these at the same time. Direct lights, static. Directional light, static. This one, static. The skylight could probably be left movable, sure. And by doing this, we are now informing the engine that we intend to do a light bake. And then the last thing we're going to do is go to build, set the lighting quality to preview, ensure that we have a volume, light mass importance volume, only framing the crucial parts of our stadium. You can see we have one, but it's actually a bit big, so I'm going to tighten it up a bit. because we simply don't need the left-hand side. We don't need all of the right-hand side. Perfect. We can also go ahead and flatten it a bit. So what I'm doing now is I'm simply framing the studio as tightly as possible with this light mass importance volume. There we go. And then the last thing we do is save. We hit the build button. We are going to build lighting only with set it to preview. And we're just going to wait for this to finish. We could, of course, evaluate our settings in the world settings as well. Ensure that force no pre-computed lighting is not turned on, because this will override a light bake and ensure that light bakes cannot be created. We can just quickly review our light bake settings to see that we have some higher bounces than default. We have quite a lot turned pretty high actually, so I'm going to go ahead and cancel my light bake. I'm just going to quickly set the bounces to 1 instead of 6, so this actually finishes within a reasonable time frame, which might be fine for just a quick test or a pre-visualizing light bake. And we're just going to restart the process. On that note, we are just going to let this tick along, but this was more or less the last subject we had for today. We've covered the video playback, which formats we can use, and image sequences versus movie files. We've looked at optimization in action. So I think at this point, as the bake finishes, we are going to take our last 5-minute break before we will go into questions and answers. So sorry about that. Yeah. So we're going to take a 5-minute intermission. We'll dig into questions and answers. So if anything has been unclear within the last 2 hours, now is your time to phrase that into words so we can get back to you and assure that everything we've gone through is crystal clear. So we'll reconvene at 12:29, 5 minutes from now. Until then. Okay, and we are back. We are ready to take in your questions. It's a little bit early, so let's wait another 30 seconds until everybody had a chance to reconvene, and then we'll get going. So this was also a complex virtual set with probably closer to 100 different lights. We are not connected to a render farm, but in this short amount of time, we were actually able to do a previous light bake for our entire virtual set. So now we can see the shadows are now finally baked. So the lights are actually baked. And if we were to do Control-Shift, comma, we can see that the overhead for lighting has now disappeared completely. And our overall frame rate, even on full screen, is now below 20 milliseconds, which means that with these few quick adjustments, we took our performance from 140 milliseconds to less than 20 milliseconds. We can also see that our bounce is a bit too low. We're not really getting any nice light bounce on the floor here of the wall. To fix that, we probably have to go in and start fine-tuning our light bake scenario. But that is an adventure for a different day. Let's actually go ahead and start with our questions and answers. So, first question is, can I have a big volume light area, for example, a big studio, and then only rebuild smaller areas of the volume light? So you would have like a big volume of baked light and then just do fine-tunements in localized areas. No, sadly you cannot. You can reduce the size of your lightness importance value, but it doesn't make sense to only bake a small section, as you would still need indirect lighting from the rest of the set. What you can do is break out this smaller subsection as a separate streaming level and bake it separately, but then you're still going to miss the interaction from the rest of your scene. It's worth mentioning that when we do these light bakes, they are global illumination, and then it lies in the name in that it's global. But you can absolutely use a smaller light importance volume in the region you want to focus on, which is going to make everything else lower resolution. So if you have a small area that you're trying to focus your attention on, feel free to box that in with a light importance volume, which is then only going to give you rock solid light bakes in that particular region of your set. Next question is, how are plane reflections assigned to each surface? For example, there are 2 levels on the floor and 2 planes. So we don't actually assign a plane reflection actor to a particular surface. The way it works is, let's take a look at it. Right now, right up here on the center podium, we have a plane reflection actor, which we can visualize outside. Let's see here. Where is it? There's a setting to allow us to show a preview plane, which you can see here. This is a preview plane for the plane reflection actor. Let's go ahead and let's turn off the distracting. Good heavens, show, visualize, there we go. So here's our plane reflection actor. The thing is, this is not actually assigned to the floor. If I move this up or down, why am I not seeing this in action? Let's take a look. Oh, I have it set to invisible, that's why. There we go. Okay, so here's a plane reflection actor, but it's not actually assigned to these surfaces. It's just, it happens to overlap because I put it there to be perfectly on top of the floor, which means that it looks like the reflections line up perfectly. If I put a cube in here, you can see the reflections look like they line up perfectly as the cube simply sits on the ground. But there's nothing stopping me from taking this plane reflection and moving it up and down, which means it's no longer actually connecting with these particular surfaces. To make it even more extreme, if the floor is not an actual plane, but let's say here, now let's say the floor is supposed to be this sphere. Notice that the planar reflection actor is now actually reflecting off the top of this sphere surface, which has a chrome material, the same way it was doing anything else. So there's no assigning, it's just you try to line up your planar reflection actor as best you possibly can with the surface that's supposed to be reflecting. On the sphere, we also see we have an angle-based fall off on the sides, which is what you can regulate with these sliders here. If we set it to 90 degrees, now we're actually getting a planar reflection on the whole sphere here. We can also set the distance fall off to be pretty tight. So now you can see there's a very visible band. Let's actually make it even tighter. Set to 5. Here you can actually see the height of the band, which is currently going to receive planar reflections. The only thing you can do in terms of manually assigning which actors should be reflected is you can't assign planes, but using the render scene primitives show on the list, this thing, you can instead say that these are the only actors I want to assign as showing up in the reflection. Now I assigned this cube. So now we can see the cube show up in the reflection here. And as I move the plane down, it will finally show up over here as well. But we don't assign these different surfaces. It's just whatever surface happens to intersect with the planar reflection actor. Next question. Are you using console because you don't have access to these options in the details panel? I'm assuming you were here asking about the ray tracing commands, and that is correct. Some of the actions I was interacting with can be accessed from post-process handler, things like screen space reflection sliders, etc. But ray tracing toggles are currently only exposed in console. But if you would like to interact with them using a control panel, it's completely trivial to make a blueprint that allows you to do that. I actually already have, not in this level, but in another level, I actually have already made a simple blueprint to deal with my ray tracing settings. In this particular set, I don't really want, this is the studio set, but optimized already, and you can see it has a blueprint called RTX toggle. Now, instead of making one input field for each individual value, instead I have a single toggle, which I can access from a control panel, which toggles a large amount of values on and off. These are the same things you interacted with through console, ray tracing, ambient occlusion, reflections, shadows, etc. What I could do instead is I could make a blueprint allowing me to control all of these manually. Let's take these 3 as an example. So here we have ambient occlusion, reflections, and shadows. All of these are console commands, which are being executed from a blueprint using the execute console command node. I'm setting the lower one to be 0, which is basically the same as turning it off, and the top one is going to be 1. There we go. Then I'm going to add a few custom events. px for peak stop, underscore RTX for ray tracing, underscore AO for ambient occlusion. I'm also going to pass in an input value, a Boolean, which is going to be turn on. And then we're just going to recycle this for the other nodes as well. Top one is px RTX ambient occlusion. The next one is px RTX reflections. And the last one is going to be px RTX shadows. The logic is very trivial. It's simply going to be a if statement. If we are passing the command to turn it on, then we're going to turn it on, which means setting it to true. Otherwise, if it's false, then we're turning it off, which means setting it to 0. We can just go ahead and use the same logic for these 3 commands. So while we wrap this up, the reason this is not exposed in the directory is because this is very much a sort of a power user setting. The average operator should never have to start fiddling with fine-tuning RTX settings. This is the artist's job. So this is typically settings you would probably try to set up in your level blueprint or in your level instead. But here with this simple setup, I could go ahead and save this. Now we have our 3 input boxes. We could go ahead and jump to the director. We can jump to our studio setup. We can edit it, and we can simply add 3 flip-flops. Then we're adding a new little segment here in our interface. Let's go ahead and add a label as well, so we can identify what these on-offs are. There we go. Ray tracing settings. Let's really give it a lovely NVIDIA green. There we go. Oh, that was very unfortunate. I'm going to leave it like that. And then we're going to have RTX AO, which is going to be left on. And if the on statement is toggled, then turn on is true. Otherwise, turn off is going to be false. Next one is going to be RTX reflections in all caps. That's going to be pointing at px reflection. And again, if this is being turned on, then the on value is going to be true. And the last one is simply going to be RTX shadows. Same thing here as well. So as you can see, within minutes, oh, yeah, I can't save it because I need to check it out. So I'm just going to open Perforce, our vision control software. And I'm just going to go ahead and check out Pixelop Studio, the control panel, which lives underneath my Pixelpalooza project. This one, check it out. So now I can actually go ahead and save it. So now, if I were to simulate this, I can now use the control panel I just created to turn parameters on and off. We're not going to see this in action because we have ray tracing turned off in the project right now, but this interface basically will enable and disable ambient occlusion, reflections, and shadows. This hopefully goes to show that if there are settings that you need that don't exist in Director, then you can easily create your own control panels to interact with any console command or custom thing within the interface you need to be able to control. Next question. What will be the best possible compression for the clip? I would definitely read up on the media framework documentation within the official Unreal documentation in terms of best practices for media. Generally, our experience is that the least amount of compression, the better. It's going to give you bigger video files, but it also means less decompression has to happen on the GPU, which means faster, more reliable playback. We tend to have more or less uncompressed H.264 encoded Matryoshka or MP4 files in our projects, unless we are using image sequences instead, where we'll be using uncompressed EXR files as image sequences. Next question. It's full moon. Okay, thank you. I'm not going to read that one out loud. I think this is more or less the questions we have time for today. So I think on this note, we're going to wrap it up. This has been a very heavy session, I'm sure. So before we hang up, next session is going to be more about the studio setup and the studio, interacting with the studio from Pixelop's point of view. It's also going to be a pretty technical session. We're going to be looking at chroma keying. We're going to be looking at green screens and how to prep them for ideal chroma keying. We are going to be doing more of a deep dive into Pixelop specific actors. And we're going to wrap it up by looking at the multi-machine setup, how to use it, how to set it up, and how to operate it. I think that's going to be it for today. Thank you for joining us. We wish you all to stay safe, stay healthy, don't go outside. And we're hoping to see all of you tuning back in tomorrow. Thank you so much. It's been a pleasure, and have a good day.